welcome to chapter 2, video number 4 in the three-phase induction machine course. In this video, we are going to cover examples on the equivalent circuit. Let's start. Before we start the examples, let me remind you about the equivalent circuits we covered in video number 3 in this chapter. So we had 3 circuits. One of them is per phase exact equivalent circuit referred to the stator, this one. We have stator impedance, we have magnetizing branch, and we have rotor impedance. And we have first approximate equivalent circuit, this one. We shift the magnetizing branch to the supply side, this one here. And then second approximate equivalent circuit, we neglect this magnetizing branch. So which circuit I'm going to use when I'm going to solve examples? So usually we use first or second approximate equivalent circuit. If we have any information about R core and XM, so we should use first approximate equivalent circuit. If we don't have any information about R core and XM, we are going to use second approximate equivalent circuit. So when we're going to use the exact one, we're going to use that one when it's frankly mentioned in the problem, use the exact equivalent circuit. Example number 1. A 4-pole star-connected 380-volt line RMS value, 50 Hz supply, 3-phase induction motor, has the following parameters per phase. Stator resistance equals 0.5 ohm, rotor resistance equals 0.75 ohm, leakage reactance in the stator equals leakage reactance in the rotor equals 1.75 ohm, core resistance equals 1000 ohm, and magnetizing reactance equals 250 ohm. Definitely all the rotor parameters are referred to the stator. For a slip 0.05 or 5%, we need to calculate using exact first approximate and second approximate equivalent circuit, the stator current, input power factor, and rotor current. And we need to comment on the results. So given this problem that the number of poles P equals 4, and the frequency is 50 Hz if we need to calculate the synchronous speed, but the supply voltage 380 volt line RMS and the machine is star connected, so we are going to say that V phase should be 380 over root 3, and we're going to choose that one with angle 0 volt. So we have all the parameters, so now we can start by the exact equivalent circuit, labeled by all the parameters. We have the supply voltage 380 over root 3, angle 0, and we have stator impedance, we have rotor impedance, and magnetizing branch. But we notice something here. In the heading of the problem, X leakage stator equals X leakage rotor equals 1.75. He didn't put here J, so you need to do that one by yourself here. You need to add J. The reactance should have the imaginary part. So that one is not inductance in Henry, so that one in ohm, so you need to add J in the stator, in the rotor, and in the magnetizing branch. So how to solve this problem? We need to find the rotor impedance first. So that one will be the rotor impedance. So the rotor impedance is 0.75 over the slip 0.05 plus J 1.75. It gives you this impedance in rectangular form. So we can convert it to polar form. If you remember chapter number 0, I showed you how to convert from rectangular to polar and vice versa. So we have this value in both rectangular form and polar form. And we notice here that magnetizing branch, the resistance of the core is in parallel with the magnetizing reactance. So we need to end up by one impedance like R and JX. So we are going to take the parallel equivalent for these two impedances. So we call it Z node, where 1000 multiplied by J250 over 1000 plus J250, Z1, Z2 over Z1 plus Z2, give you this impedance in polar form and rectangular form if we need it. So between points A and B, we're going to calculate the impedance for this side. So we notice that rotor impedance and magnetizing branch are in parallel. So the rotor impedance is in parallel with the magnetizing impedance, and the parallel equivalent is Z1, Z2 over Z1 plus Z2, gives you this side impedance will be in polar form and rectangular form. Now I need this one, because this one will be added to the stator impedance to have the total impedance seen by this source. So to have the total impedance, we need to add the stator impedance with the parallel combination between the rotor impedance and the magnetizing branch. The total impedance is 15.63 angle 15.9 degree ohm per phase. So to calculate the stator current or the motor current, so we are going to divide V phase over Z total, and we are going to find that the total current or the stator current is 14 ampere roughly, and angle minus 15.9. Negative because the current is lagging the voltage, and the current here is lagging because the motor is an inductive circuit. What about the power factor? The power factor is cosine theta v minus theta I. Theta v is 0, theta I is minus 15.9, so that one will be cosine 15.9.962 lagging. What about the rotor current? To calculate the rotor current, we need to use a current divider rule in this circuit. We have I stator here, which is this value. So we are going to divide that one between this branch and this rotor impedance. So we are going to multiply I stator by Z node over Z node plus Z rotor. So let's look here. So I rotor equal I supply multiplied by Z node over Z node plus Z rotor. In this case, you are going to find that I rotor equals 13.71 angle minus 12.64 ampere. What will be the case if we solve the problem using the first approximate equivalent circuit? The first approximate equivalent circuit looks like what we can see here. We shifted the magnetizing branch to the supply side, so we can calculate I rotor directly. And to calculate I node, we can calculate I core and IM. So the equivalent rotor and stator impedance, if we add those together in series, will be Z stator plus Z rotor. So that one will be 15.5 plus J 3.5. And that one ends up by 15.9 and angle 12.72 degree ohm per phase. So now we can calculate the I rotor directly. So I rotor will be V phase over Z stator plus Z rotor, and that one will be in the polar form 13.8, and in the rectangular form will be 13.46 minus J 3.03 ampere. Fine, so we calculated the rotor current. So how to calculate the no-load current? We need to calculate I core and IM. So I node equals I core plus IM. So I core equals V phase over R core. So that one will be 380 over root 3 over 1000, give you 0.2194 ampere. And V phase over XM gives you IM. That one will be minus J. Don't forget minus J. Minus J 0.878. So here I put 250 angle 90. So that one will be minus J 0.878. So I node will be the addition of these two components. So that one will be I node in the polar form will be 0.91 ampere, angle minus 75.95. And please note that no load current has angle close to 90 degrees. So this circuit is more inductive circuit. It's not more resistive circuit. And here we have that one in the rectangular form. So if we add I node to I rotor, we can get I supply. To calculate the supply current, we are going to add the no-load current and rotor current in the phasor form. So the current equals 13.7 minus J 3.9 ampere in the rectangular form. In the polar form, it will be 14.22 angle minus 15.95 degree ampere. So what about the power factor? The power factor will be cosine theta v minus theta I. So will be cosine 15.95, which equals 0.962 lagging. So we can solve the problem using second approximate equivalent circuit. So the second approximate equivalent circuit, we're going to ignore totally the magnetizing branch. And in this case, I stator equals I rotor, and we solve that one using the first approximate equivalent circuit. So directly you can calculate Z stator plus Z rotor, and then the rotor current will be the same value as the rotor current in the first approximate equivalent circuit, 13.8 angle minus 12.72 degree ampere. So if you notice here that when we solve the exact equivalent circuit, we calculate the total impedance, then we are going to find the stator current, then we are going to distribute the stator current to find no load current and rotor current. While we are going to solve using first approximate equivalent circuit, we're going to find the rotor current first, then we're going to add it to the no load current to find the stator current. For the second approximate equivalent circuit, we're going to find the rotor current, which equals the stator current. In the heading of the problem, he asked us to comment on the results, so we are going to make a comparison between the results for the exact first approximate and second approximate equivalent circuit. So I'm going to tabulate the results here. We have stator current, input power factor, rotor current for each case. So if you notice here, we have a stator current 14.03 ampere in exact solution, and for first approximate equivalent circuit 14.2, which is so close, the error is minimum. And that one leads to the power factor almost the same, 0.962 lagging. While the rotor current in the exact solution will be 13.71, and the first approximate equivalent circuit will be 13.8. But between first approximate and second approximate, the rotor current will be identical, which leads the stator current will be similar to the rotor current in this case. And because we take in the rotor current as a stator current in the second approximate, the power factor is slightly different from first approximate or exact solution. So we are going to highlight some comments here. Shifting the magnetizing circuit to the supply side is a valid assumption. We accepted minimum error here, but that one when the machine is loaded, right? So that one is accepted, and that one saves us a lot from manual calculation. If the magnetizing circuit is neglected, totally neglected, the rotor current is considered as a supply current. We can consider that one is accepted solution as well if the machine is loaded. But if the machine is going to operate close to the no load conditions, second approximate equivalent circuit is not accepted because rotor current will be zero while the machine takes current, and the stator current in this case will be the no load current. So the machine will take magnetizing current irrespective of load or no load conditions. Let's have another example. Example number 2. A 415 volt line RMS value, 50 Hz, 4-pole, star-connected squirrel cage induction motor has the following parameters referred to the stator side at standstill per phase. So he gave us our stator, our rotor, X leakage stator, X leakage rotor, and magnetizing reactance, and our core is neglected. But it's first time to hear the word standstill, so we need to know why he mentioned this word. He said that for a specific slip of 2.5% at rated voltage and frequency, we need to calculate rotor speed, rotor current, stator current, and motor power factor. So which equivalent circuit we are going to use? He gave us information about R core and XM. So in this case, either we are going to use the exact equivalent circuit, but that one is going to complicate the analysis. So we need to make that one an analytical solution. So we're going to use first approximate equivalent circuit. And first approximate equivalent circuit, as we see in this figure, but R core is neglected. So we have the stator and rotor impedance are together. So R stator, JX stator plus X rotor, and R rotor over S. Please note that X stator and X rotor in the heading of the problem has no J, so you need to add the J by yourself. But we know that R rotor is R rotor over S for a specific S. What is R rotor value, physical value for R rotor? So if S equal 1, so we know what's R rotor. So this is why he said at standstill. When the motor at standstill, this means that when S equals 1. So R rotor over 1 equals 0.32. So now we know what's R rotor. So given now, the machine is 4 poles, star, line value 415. So if we like to calculate that one as a phase value, so that one will be 415 over root 3 angle 0. We're going to assume that one as angle 0. And give us the parameters. R core is infinity, XM is J28, so that one should be J as well. And we have here J.9 plus 1.1, and we have R stator 0.64, and now R rotor over S is 0.32 over S. So part A, he wants to calculate the rotor speed. To calculate the rotor speed, we need to calculate the synchronous speed and we need to know the slip. So the synchronous speed is ns equal 120 fs over p. Fs is 50 hertz. P is the number of poles equals 4. So ns equal 1500 rpm. If you like to calculate angular synchronous speed, omega s equals 2 pi ns over 60. So that one gives you 157.1 radian per second. We know S equals 2.5% or 0.025. Please take care of this zero. So that one is 0.025. So NR equals NS 1 minus S 1500 multiplied by 1 minus 0.025 gives you 1462.5 RPM. If you like to calculate the rotor speed, angular rotor speed, omega R equals 2 pi NR over 60. That one will be 153.2 radian per second. So that one is a straightforward, and we did that one before in the previous video. For part B, it's required to calculate the rotor current. As we have information about the magnetizing branch, we're going to use the first approximate equivalent circuit. The phase voltage is 415 over root 3 angle 0 degree. We choose the angle to be 0. And the slip is 2.5% or equals 0.025. So the total impedance for this side will be R stator plus R rotor over S plus JX equivalent. So stator and rotor impedance equivalent will be 13.6 angle 8.5 degrees ohm per phase. So the current is V supply over impedance Z. So that one gives you 17.62 angle minus 8.5 degrees or 17.43 minus J2.6 ampere in the rectangular form. To calculate the stator current, we need to calculate the magnetizing current. In this circuit, the magnetizing current is V phase over JXM. So that one will be 415 over root 3 over 28 angle 90 degrees. So the current IM will be minus J 8.56 ampere. Now we can add I rotor plus IM to have I stator. So the stator current in phasor form will be IM plus IR. So we add IR plus IM. That one gives I stator in rectangular form 17.43 minus J 11.16 ampere. Or in the polar form, we have 20.7 angle minus 32.6 degrees ampere. So for the last part, the motor power factor will be cosine theta V minus theta I. So that one will be cosine 32.6, gives you 0.842 lagging power factor. In this example, it's clear now that analytical solution is straightforward, how to calculate the rotor speed, the rotor current, and the stator current. How we make sure that our solution is correct. So I'm going to use simulation using MATLAB Simulink, but we don't know anything about simulation yet. I'm going to explain that one in details in chapter number 5. But I'm going to use a simulation to confirm the results I had. So here we have rotor speed 1460 RPM, and the stator current equals 20.46 ampere with angle minus 30.11 and the rotor current 17.9 ampere. If we simulate the waveforms, we're going to find that the rotor speed at steady state will be 1460 RPM and the stator current has a peak value 28.9, which is something like 20.46 ampere as RMS value. And the rotor current is 25.3 ampere as a peak value, which is something like 17.9 ampere RMS value. Why there is a difference between analytical solution and simulation? Please remember that we solve the problem in the analytical solution using first approximate equivalent circuit, but simulation using the exact equivalent circuit. So this is why you find the difference between analytical and simulated one. Another thing I need you to notice here, that the stator current has a frequency something like 50 hertz. So we have time, periodic time here equals 0.02 second. So the frequency F stator equals 50 hertz. And that one is the stator current. But for the rotor one, we have here waveform with time here something like 0.8 second, where FR equals 1.25 hertz. So slip equals FR over Fs, which gives you 2.5% or 0.025. So now the simulation confirms the analytical solution. So now it's time to give you an exercise to test yourself. we have a 230 volt RMS value, 50 hertz for poles, delta connected. Squirrel cage induction motor has the same parameters we had in the previous example. So also we have XM and R core is neglected. So definitely are going to use the first approximate equivalent circuit. But the slip now is 4% at rated voltage and frequency. So we need to calculate the rotor speed, rotor current, stator phase and line current because we are delta connected. So we now can have stator phase and line current. And we need the motor power factor. So once you solve the problem, we can check your answers with the final answers. But if you notice here, we have the rotor speed, rotor current, stator phase current with angle minus 29 degrees with respect to the supply, which is angle 0. And the line current is root 3, the phase current, and the angle is minus 30. So minus 29 minus 30 give you minus 59 degrees. And the power factor is cosine theta v minus theta I. If we choose 230 volt, which is line value equals phase value in the delta connection, so that one was angle 0, so theta v is 0, and theta I is minus 29, so the power factor is cosine 29 degrees, which is the angle theta v minus theta I for phase values. So that one gives you 0.875 lagging. Please solve the problem and check yourself. Let us summarize chapter 2. We delivered this chapter in 4 videos. So in this chapter, we offered highlight about induction machines. We explained the construction of the induction machines from an industrial perspective. We explained the machine labels and terminals and how to connect the machine as a star or delta. Also, we looked for the slip speed concept for the motor operation. We looked for the theory of operation, or we explained the theory of operation in details, and from the theory of operation, we deduced the equivalent circuit, exact first approximate and second approximate. We ended this chapter by some examples about the slip concept and motor equivalent circuit. Now, what will I watch in the next chapter? In the next chapter, we are going to cover 3-phase induction motor power and torque calculation. See you in the next video.